Okay, everyone, welcome to the final session, if you're not too waterlogged. As a special treat, we have arranged for the rain to stop during this session, I'm told. We're straight on to Ricardo, who is going to tell us about the resurgence of negativity.
Okay, thank you. Thank you very much, and thank you very much to the organizers for inviting me. It's a pleasure to be here. And I want to talk about resurgence and negative tension in deep brains. This is work that mostly it's appeared the past couple of years, and it's going to appear sometime soon. We're in the writing now, which is mostly done with my students who are also around, and hopefully you've talked with some of them. So what do we try to do when we apply resurgence to string theory? Well, we're trying to find a construction of non-perturbative string theory, not a definition. So there's sort of a dichotomy that you can think of, definition, construction. All we're going to focus upon is a construction. So string theory is usually given as a sum over surfaces of different genera, an expansion in the strict coupling GS squared, and the genus G free energies, which may depend on some moduli describing the string background you're in, they grow asymptotically fast. So basically we cannot resum the perturbative expansion, so something we must do. What we know we must do is to look at non-perturbative contributions. We must find a way to include them. So on top of these G-string monomials, there's going to be non-perturbative stuff that looks like exponential of -1 over GS that we need to add to this series to make it well-behaved and to compute. For that to happen, however, using resurgence, we need to have the perturbative expansion under control, so we can ask, when is this possible? Which class of backgrounds can we look at? Well, there's actually many backgrounds we can look at. The string theoretic perturbative expansion is under control basically when there's some sort of random matrix model underlying the background I'm looking at. And that was the case in the 90s with multi-critical strings, in the early 2000s with minimal strings, and later on with Hermitian matrix models and their topological string duals, up to recently with JT gravity. The reason why the perturbative expansion is under control in the system, or let me say it again, I already said that. The reason why we can take the perturbative expansion to high order in the systems is because we no longer have to deal with conformophile theory in the world sheet. We heard on Wednesday afternoon, if I'm not mistaken, that going beyond genus 2 is hard, but here it's not, because we have alternatives. We can use string equations, we can use the topological recursion, the holomorphic anomaly equations. There's other alternative methods to obtain both perturbative and non-perturbative data straight out for these backgrounds. So then we can ask again, how can we do this non-perturbative construction of string theory? Again, no definition. Well, we look at the resurgence of this perturbative series, and from that we can extract the full non-perturbative resurgent trans series. So a word on resurgence. What is the resurgence program or construction sort of doing? We start here on the bottom left with our asymptotic series. Again, this is our free energies at genus G. They're factorially divergent. And what we do is a Borel transform. What the Borel transform does is a machine that removes the factorial growth, only leaves exponential growth, which is well-behaved, and so we obtain a convergent series. So the thing we would like to do after is the dashed arrow. Just invert the Borel transform, which is given by a Laplace type integral, and obtain a result. That, however, which would be this one, not so fast, because this series is convergent around the origin, but it has singularities. If there were no singularities, there was no asymptotic series to start off with, so we have to deal with these singularities. In all this class of backgrounds that we're looking at, singularities are all of the same type. They're known as simple resurgent singularities, which are logarithmic. There's some more stuff there, which is holomorphic. The singularity is logarithmic, and there's also some holomorphic dependence in front of the singularity. We usually split it into some normalization factor, a number which is associated to Stokes data, and a holomorphic function which we look at as the Borel of something else. Okay? And then when we do that, we can do the Borel Laplace transformation, because now we know where the singularities are, and we know where we can do that integral and where we cannot. Well, where we cannot do that integral is along Stokes lines. So this is the Borel plane, and those black dots represent Borel singularities. So the dark blue resummation is not equal to the light blue resummation. The difference is the sum over all these Hankel contours, which is easy to evaluate for this type. I mean, the log on the Hankel contour just have a jump, and then I have the Borel of something else, which is a trivial to invert. So it's easy to actually compute this difference, which I will call this discontinuity. It's basically a sum over the singularities of Stokes data, our transmonomials, exponential of -1 over GS, and the something else. So the something else must always be there, because if I just start with a perturbative solution and then go around the Borel plane, eventually, hey, we're here, and I need to take them all into account. Now, when we look at string theory problems, there is a novelty, which is that the string expansion is an expansion in powers of gs squared. But the leading non-perturbative contributions are of the type exponential of minus 1 over gs. What that implies is that the Borel transform has fixed parity. The singularities on the Borel plane are always symmetric. This guy has the technical name of resonance in the Resurgence literature, but this is the plot of the Borel plane for JT gravity, numerical, and we see that singularities are always symmetric. So we would like to first see how this comes about, and then give them an explanation. So this was first seen in the context of string equations. So we've solved many examples. Here's the simplest possible example one can think of, which is the 2,3 minimal string theory, which is described by the Pauli-Level equation. That's the Pauli-Level equation. It's a nonlinear second order differential equation where U is the specific heat, so I obtained the free energy real fast, and Z is basically the string coupling. Now in the 90s, people already looked a lot at these perturbative expansions. It was more recently in 2010 that people started looking at the non-perturbative contributions, and those are the instanton actions in this problem, so they're clearly symmetric. The full solution can also be written down. So this is the full solution to Pauli-Level 1. Again, we can write down full solutions to other examples, but let's just focus on the simplest possible case. For the specific heat, again, because the equation is second order, I need basically two boundary data or two initial conditions, which are the transseries parameters sigma 1 and sigma 2. Then I find that because the system is resonant, in other words, because there's a plus and a minus instanton action, that there's terms that look like that, n minus m. And then there's a bunch of asymptotic sectors. There's some log sectors, but they're not independent. It's not important. So let's just focus on that. There is a curiosity, however, which if I have time, I will speak more about in the end, which is when n is equal to m, we have a bunch of non-perturbative sectors, which are neither exponentially suppressed nor exponentially enhanced. They're order 1. So, you know, you can see these in many examples. We've looked at multi-critical models, minimal strings, Hermitian matrix model, JT gravity, you name it. And the bottom line is always the same. There's more sectors than you would naively expect. You no longer have, or you not only have the perturbative expansion plus exponentially suppressed stuff, there's exponentially enhanced stuff, and there's non-perturbative order 1 stuff. So the question is, what are, from a semi-classical point of view, these new resonance sectors? So we go back to the plot that we've looked at, and I not only want to explain what is that singularity, the singularity on the positive real axis on the Borel plane, which is easy, but I also want to explain that other singularity, which actually turns out also to be easy. And let me just immediately tell you what it is. So the singularity of the positive real axis is described by either eigenvalue tunneling or de Bruijn. So what am I plotting here? This is a matrix model, and this is the spectral curve of the matrix model. So it has a cut from A to B. Let's say it's an elliptic curve. It's the cubic matrix model, and has a pinched cycle where I remove eigenvalues too. And this was done in 92, if I'm not mistaken, by François David, where it looks at what happens if I remove an eigenvalue from the cut and I put it at the pinched cycle, and I get the contribution, which is exponentially suppressed. Okay, we've known that for 30 years. The same with 94, Polchinski, de Bruijn. This is just a cartoon of a de Bruijn. And so all these things describe that singularity. What about that singularity? Well, it turns out that it's not much harder. The exponentially enhanced contributions come from tunneling not an eigenvalue, but an anti-eigenvalue, or if you will, an eigenvalue on the non-physical sheet of the spectral curve of the matrix model. And that basically, the fact that the involution map, as I will show you in a second, flips a sign is enough to change that. In string theory, what we have is negative tension de Bruijn. It's just a cartoon. I mean, there's a color coding to the cartoons. And negative de Bruijns are not new. People have looked at them in the literature. But here, the point is that they're a requirement of resurgence. If you're going to be looking at the GS squared expansion of string theory, you have to deal with them. So let's see how they appear first in the matrix integrals and then in the de Bruijn calculation. So in matrix integrals, what we would like to do? Well, we go back to our trans series that came from the string equation. Roman Z says stuff that came from the string equation. I'm just writing to the partition function. That's it. And then I look at matrix integrals. This is slightly curly Z. And this is the one matrix model. That's all we're doing. And here's are the eigenvalues associated to the random matrix M. And they have some contours. So what we would expect to happen is that different choices of contours would lead to different contributions to the trans series. So which sectors are associated to which contours is the question. And I'm just going to tell you why weird contours are going to appear and then just show you the calculation in a cartoon. The reason why is because I want to move from the physical sheet of the spectral curve to the non-physical sheet of the spectral curve, which is accomplished by the involution map. At the level of the xy coordinates in the spectral curve, it's very simple. It's a seemingly harmless minus sign, but if you look at determinant correlation functions, which I need to use in order to compute non-perturbative contributions, it turns out that actually the determinant gets flipped by the involution map. The n minus 1 gets n plus 1, and those exponentials also change. So basically, taking an eigenvalue through the involuted sheet behaves like a hole on the physical sheet, and so these are basically anti-eigenvalues. So instead of showing you the computation, let me just show you a plot. What's going to happen is that I wanted to describe the Stokes jump, the Borel singularity on the positive real axis, and I already know since the 90s that what I do is, let's say that I have the cubic matrix model, that's the potential, I have n eigenvalues on the cut, I remove one eigenvalue, I place it at the pinch cycle, and that gives me the e to the minus n contribution. So what we're doing here, when we want to describe the Borel singularity on the negative real axis, is we create a pair, eigenvalue, anti-eigenvalue, hence the n plus 1, which appeared here. And then I remove the anti-eigenvalue and I place it at the pinch cycle. And this is going to give me the e to the plus n contribution. Now this is not just minus signs, because the full train series has a lot of non-trivial sectors where there's both eigenvalues and anti-eigenvalues. And what this will imply is that many calculations on top of doing steepest descent on the matrix model, I also have to do residue calculation. Can I do the same calculation using D-branes? Well, yes. Let's look at an example involving minimal string theory. So basically, a minimal model, Liouville, ghosts, and the string theory requirement. What are the usual D-branes that we find in minimal string theory? There's FZZT D-branes. Here's the disk. They're labeled by a complex parameter zeta. And you can compute the disk amplitude as an integral over the moduli space of the FZZT, and this is an example for the 2,5. And in blue, we sort of see the FZZTs. This is not the whole content of Liouville D-branes. There's also Liouville ZZ branes, and they're labeled by two integers, which, well, they're not free to roam around. They're constrained to basically to the pinched cycles of the moduli space. So how would I compute the same contributions now from the point of view of Liouville theory? Well, what I would like to do is compute basically this sum. So we know that the D-brane combinatorics exponentiates, and that I have to compute. Now I have ultra curly Z, that's stuff that comes from BCFT, and that the contribution to the partition function is going to be an exponential of the sum of disk, annulus, and so on of ZZ branes. Now, the disk is actually not so hard, and if you do the calculation with a negative tension, you just get the trivial minus sign, and you say, this is completely harmless. The annulus is harder because the annulus requires regularization, and in fact, the proper regularization of the ZZ annulus has only been done recently, 3 or 4 years ago, by Ashoksen and collaborators using string field theory, so it's not necessarily an easy calculation. But there's a slightly simpler calculation that one can do, which is to recall that ZZ branes can be seen as differences of FZZTs on the different sheets. So, too many. So you see, the ZZ can be seen as a difference of the FZZTs. And if that's the case, then we can write down the same ZZ contribution as this difference, integrating over the moduli space of FZZTs at the saddles. And then I'll have a difference of the disks, a difference of the annuli, and so forth. The reason why this calculation is simpler is because we do know also the FZZT annulus also requires regularization, but we do know how to do that regularization for 19 years now, since Kutazov, Okayama, Park, Seiberg, and Shi. And so that's actually an easy regularization. It basically gives you a log x squared, roughly. Now, what's going to happen is that if I compute the contribution that comes from a ZZ brane and the negative tension ZZ brane, I get my exponential with all those terms. Now, I'm not putting those plots anymore because they just don't fit. And the regularization, which normally, when I just have ZZ branes, would give me a log x squared, and so in the exponential would make an x squared term come out. Now, with the negative tension D brane, has an overall minus sign as well, which is no longer just harmless, because it's inside an exponential, which means that there's going to be an inversion, and an inversion at the level of the integrand. So I get the 1 over x squared. And so this minus sign, which was previously harmless, is now no longer harmless because the integration I'm going to have to do involves residues. And, well, you do the computation, and this is what you find. This is the punchline, so let me not bore you, nor there is time to bore you with calculations, because some of these matrix integrals occupy literally pages of LaTeX on how they're computed. But whatever you get out of string equations exactly matches whatever you get out of matrix integrals once you account for the fact that you have both eigenvalues and anti-eigenvalues going around. And everything also matches with what you get out of D-brane calculations once you account for the fact that you have both standard D-branes and negative tension D-branes. So in principle, that's all there is to say for the non-perturbative content of these models. So you can ask, and you should ask, well, now if you have all the perturbative contributions, all the non-perturbative contributions, can you write down exact solutions for string theories in these backgrounds? Well, the answer is yes. And they actually look quite simple. So if we include all anti-eigenvalues or negative D-brane contributions, there's a closed form expression for the full train series. Okay? So let me explain you so this is an exact solution, and I'll show you some plots next. So let me explain the different contents. So I'm looking at the most general class of all these particular backgrounds I mentioned is looking directly at the Hermitian 1 matrix model. The Hermitian 1 matrix model depends on T. That's the 't Hooft modulus. And I'm computing the partition function train series. Oh, sorry, one too many. Partition function train series for the one-cut problem. And the train series depends on train series parameters, as I said, sigma 1 and sigma 2. And they actually simplify, they appear always in this product to some extent, which I will call mu. And so that's the matrix model with a 't Hooft modulus and train series parameters. The solution is sectorial. The reason why the solution is sectorial is because there are Stokes transitions. So each piece of the solution lives in a different Stokes wedge. And I will need to glue it using Stokes data. So I'll say nothing about Stokes data in this talk, except that it has to be there. This sectorial solution is written as a discrete Fourier transform, where the Fourier parameter, rho, is written here. So it depends also, I keep pressing the wrong button. It depends also on the train series parameters, and it involves on, so this particular formula I'm writing here is for the case of the 2,3 minimal string, because it depends on Stokes data. And this is a Stokes coefficient, and this is the generating function of Stokes data for that particular problem. We know Stokes data for all these other problems. I don't have time to talk about it, but so we can always write down the Fourier parameter. And then it's the exponential of the free energy of a two cut. So I have to open up a second cut on the problem I started, and I only use the perturbative contribution where the train series parameters have been upgraded to two-cut moduli. So they're now moduli of the two-cut problem. And all I have to use here, well, there's a regularization, which is not important. All I have to use here is perturbative data. And if I put perturbative data on this generalized background where I've opened up a second cut, and I identify train series parameters appropriately, I claim that this is an exact solution to the problem. So let me show you, using some data, how we can go arbitrarily strong coupling and arbitrarily quantum. So to solve matrix models, one way that you can do it is by using orthogonal polynomials. And to generate orthogonal polynomials, you need those recursion coefficients, which satisfy string equations for different problems. So for the quartic matrix model, it satisfies this nonlinear recursion. And then I can obtain a partition function as well from those guys. So if you just plug in the computer the matrix model and you ask it to solve it, this is the logarithm of these coefficients r's, and this is the argument. And what I'm showing, I'm plotting you the log and the argument of those guys as I vary the 't Hooft coupling. And they have this behavior. The first thing you could ask is, why is behavior regular and then jumping around? The reason why that happens is because there's different large n phases for your matrix model. The different Rn behavior is associated to different phases on the 't Hooft plane. There's the gray phase, there's the green phase, and there's the pink phase. There's actually oscillation start already there. So, I mean, this is not a misplot. You just can't see it because of the resolution of this plot. And so, what are these phases? This is also quite well known in matrix models. So, if I show you the phase diagram of the quartic matrix model, this is the 't Hooft coupling, complex 't Hooft coupling, and I have different phases. This is where eigenvalues accumulate. And here, this dashed, solid dashed line is basically what I'm showing you here. So I'm going around, this is the trajectory I'm taking on the 't Hooft plane. And I go through different phases. I go through the gray phase, where eigenvalues cluster on a cut. I go through the green phase, where eigenvalues cluster on 3 cuts. And then I arrive at the pink phase, where eigenvalues cluster on a trivalent phase. That phase is not important. You could go through there, but I'm just not showing it. And here's our solution can see all phases. That's the red line. Again, in order to do this, you have to glue sectorial solutions. Stokes data is relevant to know how to glue. In fact, that's a Stokes line over there. How to glue the sectorial solution to the sectorial solution, but I can go from weak to arbitrarily strong coupling, and I can have an exact interpolation on the 't Hooft plane. So this is not only true at the level of the 't Hooft coupling, this is also true quantum mechanically. So here I'm showing you again the same thing, the RNs, the real part and the imaginary part. And what I'm varying now is n. 1 over n is GS, or h bar if you want, and then goes from 100 to 0. So this is like highly quantum. Highly quantum. And you see that we have the black dots that come from evaluating, if you want, the 1-by-1 matrix model, the 2-by-2 matrix model. And the red line interpolates everything in the different phases, in the gray phase, in the green phase, in the pink phase. And this is not as boring as it might look like, so that's why we zoomed in to show you that we were almost at infinite h bar, and still we're hitting everything right on. And, we can do more plots. Let's not worry about that. So I have 5 minutes, so let me just end with one lingering question, which is, what happens on that diagonal? On that diagonal, I have a bunch of non-perturbative sectors, which yet are order 1. So what could that be? Well, if you actually look at the calculation and the data, and let's look at the free energy, and we focus just on the terms of diagonal, let's disregard the exponentials. This is what it looks like. This is the contribution. And it turns out that the contributions in GS that appear in these terms, all these 0, 0, 1, 1, 2, 2, 3, 3. If you expand them out as asymptotic series, their GS contribution is of this type, 2G plus H minus 2, and trans-series parameters appear like that. And anybody should recognize this sum. This is just like an tough sum to be done, where now what I am doing is not basically just summing over d-branes, but d-branes and negative tension d-branes, which are sort of condensing on the diagonal to give rise to a closed string theory, which now has an extra modulus. So this Etov-like parameter has been upgraded to a modulus of my other string background. So this was already sort of given away in the exact solution that I wrote 2 or 3 slides ago, but now it's more clear. And so the point of what this diagonal is actually doing is encoding all other possible, in this case, multi-cut backgrounds that the system starts off with. You start off in a 1-cut, which was also clear when I showed you, by the way, the picture as you move around in the 't Hooft plane. You see not only the background you started off with, but by including all non-perturbative contributions, you see all other possible backgrounds. So the full non-perturbative partition function, the exact solution, is background independent, as it better be. On top, there's a bonus, which is that this prepotential of these multi-cut backgrounds actually matches the prepotential of Argyris-Douglas theories, just because of the fact that that's how the Seiberg-Witten curve becomes just the curve of the matrix model. And so you can describe these prepotentials of these specific Argyris-Douglas theories, which we heard about yesterday morning, in terms of topological gravity or emission matrix models. And this is basically generalizing the Paulin-One gauge theory correspondence from just the Paulin-One equation to the full KdV hierarchy, and to any Hermitian one matrix model with potentials of degree k+1. On top, there's also a bonus, which is that as we create this Argyris-Douglas series, the resurgence comes along for the ride. So I no longer have just the resurgence of the string theory expansion, which I told you about, which is just the standard resurgence of the GS² expansion, but I also get for free wall-crossing formula of the Argyris-Douglas theory. This is associated to the fact that when I open up other cuts and I see these other backgrounds, these cuts start their lives as a conical point, and then they sort of grow into full-fledged cuts, and I get a second Stokes transition. I not only have the standard Stokes transition associated to string theory, but I get the Stokes transition associated to the conifold, and when these guys cross on the Borel plane, they give rise to the wall-crossing formulae of the Argyris-Douglas theory. So I think my time is up, so let me just conclude by saying that these negative tension d-branes are there, these anti-eigenvalues are there, because basically that's the way that you check that everybody matches in the solutions that you can construct to string equations. And then when you write down exact solutions, you also see that in order to go from this gray phase to this green phase to the pink phase, you either include all these people or you just don't match the numerics that you get from evaluating 1 by 1 or 2 by 2 or 3 by 3 matrix models or whatever you want. And then as a bonus, these exact solutions that we write down, they display background independence. So, I mean, they're, nice non-perturbative objects as we expect, non-perturbative solutions as we expect to find in string theory. And they give us the bonus of describing also some results on Argyris-Douglas series and its wall crossing. Thank you very much.
Thank you. Do we have any questions?
I want to suggest an alternative interpretation to your negative tension d-branes. I mean, suppose you are working with a complexified world volume such that you rotate the world volume coordinates by e to the I phi 1, e to the I phi 2, such that the sum of the phases sums to 2 pi. Then you would get that the dBi action reverses sign.
Yes.
So do you have necessarily the interpretation of the negative?
I think we have necessarily the interpretation of the negative because of the annulus diagram. If all we had to look at was the disk, then I would say, okay, maybe. But once we go to the annulus, then I say, no, I don't think so.
I have another question. For the Veneziano amplitude.
Sorry.
For the Veneziano amplitude,
Yes.
should I also add e to the plus 1 over g stream?
Maybe. We haven't looked at correlation functions. I have some students looking at correlation functions, but
Yeah, I think I have a little bit general question.
Yes.
What is the physics of the negative tension branes?
So, well, for that I don't have an answer because we're not looking at negative tension d-branes in isolation. We're looking at the contribution that negative tension d-branes have for the partition function. And the physics is the one I told you about, that you see different phases in the matrix model. If you want to look at negative tension d-branes living their own life alone, that we have not done.
But do you have a guess, or do you think it's impossible to? Is it in a sense some sort of confined within the entire theory, or is it impossible to see them in isolation? Or?
I don't think it's impossible to see them in isolation once you go to complex values of your moduli. But at real values, they would be very unstable. Yes.
Well, I mean, naively, they seem to destabilize the theory completely, right?
Yeah.
Yes.
And by the way, there's also negative tension Fs at T.
Hi. I wonder if you had any comment on the interpretation of those contributions to topological strings from the M theory point of view, like from the M theory point of view,
yes.
like Gopak-Kumavafa type things, especially. And I wonder, by the way, if you can, if that, this contribution supposedly in those recent work by Haddad and Palti, they were claiming, I think, that they could see a lot of the resurgence results from. Yeah, if you have any comment on that.
I have not thought about that. I'm sorry, I don't have it.
But in terms of just the M theory interpretation of these anti-dipole.
I mean, at the end of the day, we're doing minimal string theory, so M theory is quite far away. I mean, you'd have to look at this there's this three-dimensional version of M theory, but we haven't thought much about it.
Hi, this might be the most naive question, but what happens when the G string goes to zero limit if you have these objects?
In the G string goes to zero limit?
Yes.
What do you mean, what happens?
Well, I would have thought if you have e to the 1 over g squared, that blows up, no?
No, the 1 over g has... Oh, the exponential terms, you mean?
Yeah.
No. I mean, everything resumes perfectly fine. I'm not sure which plot. So here's you see that GS is 1 over n, so it's going from 0 to infinity. Everything resumes perfectly fine. There's no.
Okay, looks like we are done. Thank you, Ricardo.
Thank you very much.